In this video, we solve problem 9.1.13-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, a simple random sample of front seat occupants involved in car crashes is obtained. Among 2,720 occupants not wearing seatbelts, 33 were killed. Among 7,783 occupants wearing seatbelts, 17 were killed. Use a 0.05 significance level to test the claim that seatbelts are effective in reducing fatalities. Complete parts A through C below. In part A, we're asked to test the claim using a hypothesis test. And then it says, consider the first sample to be the sample of occupants not wearing seatbelts, and the second sample to be the sample of occupants wearing seatbelts. Then it asks, what are the null and alternative hypotheses for this hypothesis test? In order to decide what the null and alternative hypotheses are, we need to state the claim in terms of P sub 1 and P sub 2, where P sub 1 and P sub 2 are the sample proportions for the two samples that we have. In order to do this, I'm going to share my paper with you. Okay, so in the problem statement, it says that the first population is the population that we have in which people are not wearing seatbelts. So N sub 1 is the total sample size for those without seatbelts. There were 2,720 of those in that sample. It turns out that 33 of those people that were not wearing seatbelts were killed. Now in the second population, we have 7,783 people, and those people were all wearing seatbelts. 17 of those happened to be killed. Now we were asked to designate this as the first population and this is the second population. So that means the population proportion for this sample is the number that were killed out of our total sample size. So that's going to be 33 out of 2,720. And then over here, the population proportion would be denoted by P sub 2. That's the proportion of those, or this is P sub 1 hat, excuse me, and this is P sub 2 hat. That's going to be the total number that were killed in our sample that were from the sample of those wearing seatbelts divided by the total number that were wearing seatbelts in the sample. So that's going to be 17 out of 7,783. This is the sample proportion of those wearing, those who die while wearing seatbelts, or those who died without wearing seatbelts. And this is the sample proportion of those who died while wearing seatbelts. The claim says that seatbelts are effective in reducing fatalities. If seatbelts are effective, what they're saying is, another way to say that is that the proportion of deaths while wearing seatbelts is less than the proportion without wearing seatbelts. So we're comparing the two proportions, which is expected. We just need to make sure that we're comparing them in the right way using the conventions that they asked us to use in the problem statement. The proportion of deaths while wearing a seatbelt comes from this second population. So that's the true population proportion for the second population. So we'll call that P sub 2. If seatbelts are effective, that proportion should be less than the fatality rate for the group that is not wearing seatbelts. That fatality rate is P sub 1. So this is our claim. If this is not true, this is true. Then if I'm trying to identify the null and alternative hypotheses, I look at these two and I look for the one that does not contain the condition of equality. This one has a greater than or equal to sign. So that does contain the condition of equality. This is a strictly less than sign. So that doesn't. So that's our alternative hypothesis. And then to get the null hypothesis from that, we're going to change this less than sign into an equal sign. The null hypothesis always has that equal sign there. Now, if I look for this in my list of possible null and alternative hypotheses, it's probably not going to be stated in this way. They always like to have P sub 1 first. So what they would say instead of saying this is they would say this. The null is that P sub 1 is equal to P sub 2 And the alternative is another way of stating this. If p sub 2 is less than p sub 1, that's the same as saying that p sub 1 is greater than p sub 2. So this is what I'm looking for on my lab statistics. So let's go to the website and make sure that it's there and then choose the correct pair of hypotheses. Okay, so I want the null to have P1 equals P2. And the second one is P1 is greater than P2. Up there it is. E is our choice. Great. And the next thing we want to do is compute the test statistic, and we want to round to 2 decimal places as needed. Now, in order to compute the test statistic, there's actually quite a bit that we have to compute. So I think what I will do is I will write down the formula on my paper, and then we'll write down what we need to write down in order to compute this, and then we'll use Excel to do the computation. Now remember, every time you're computing a test statistic Z, what you are doing in this lesson anyway, when you're comparing two population proportions, basically what you're doing is you're looking for the number of standard deviations that P1 hat minus P2 hat is above or below the mean, given that the null hypothesis is true. So remember how this works. For a given sample proportion, p hat, and we said that under certain conditions that p hat, the distribution of p hat, that's the sampling distribution, would be normally distributed. So this is a normally distributed random variable approximately, and then p hat 2 is also a normally distributed random variable. So when we subtract them, we expect to have a normally distributed random variable as well. And then we said earlier in the last video that the mean of p sub 1 hat minus p sub 2 hat is actually equal to p sub 1 minus p sub 2. Now what we want to do is we want to look at the distribution of p sub 1 hat minus p sub 2 hat, assuming that the null hypothesis is true. So that's assuming that p1 is equal to p2, which is the same as assuming that this mean is 0. And then we're saying to ourselves, if this mean is 0, is the p sub 1 hat minus p sub 2 hat that we got from our sample, which is this minus this, which is approximately equal to that number, is that significantly high or significantly low, given that the null hypothesis is true? So we compute that. This is the number of deaths out of the number of people in our sample that were not wearing seatbelts. And then this is the number of deaths out of the total number of people that were wearing seatbelts. And then we just subtract them and we get that number. It's very small. It's about 0.009948 approximately. So it looks to me like it's probably going to be very close to the mean, p sub 1 hat minus p sub 2 hat. And the question is, well, is that significantly high, given that the null hypothesis is true? The way we determine whether that's significantly high or not is we take this distribution of p sub 1 hat minus p sub 2 hat, and we convert it over to a standard normal distribution. And we do that in this way. Now remember, whenever you're converting from a test statistic, or excuse me, not from a test statistic, from a sample statistic like p1 hat minus p2 hat, and you're converting from that to a z-score, what you're doing is you're finding the number of standard deviations that p sub 1 hat minus p sub 2 hat is above the mean, provided that the mean of this distribution is equal to 0. And remember, if the mean of this distribution is equal to 0, that means that the null hypothesis is true. Now, in order to do that, we just take the random variable that we're interested in, we subtract the mean, and we divide by the standard deviation. That's going to give us a number of standard deviations above or below the mean. But this time, instead of using x minus the mean over the standard deviation, our continuous random variable is this p1 or p sub 1 hat minus p sub 2 hat. And then we're subtracting the value of the mean here, and the mean of p sub 1 hat minus p sub 2 hat is actually p sub 1 minus p sub 2, the difference between those two true population proportions. And then we're dividing by an estimate for the standard deviation. Now, in this distribution, we're assuming that the null hypothesis is true. So this P1 minus P2 is going to be 0 because we're assuming that P1 and P2 are equal to each other. Now in the denominator, we're going to have a standard deviation, which is also based on the assumption that the null hypothesis is true. The null hypothesis says that P1 and P2 are equal to each other. Normally the standard deviation would be this square root of P1 Q1 over N1 plus P2 Q2 over N2. But if P1 and P2 are the same value, well then I shouldn't have a P1 Q1 here and a P2 Q2 here. I should have whatever that common value is of P1 and P2. But we actually don't know the common value. The best guess, though, that we have for that common value is what's called the pooled sample proportion. So the pooled sample proportion is the proportion of successes in a larger sample. So rather than thinking of these as two separate samples, I'm going to think of them as a single sample. Rather than separating these people into groups of people that were wearing seatbelts and were not wearing seatbelts, I'm going to think of this as a group of people. And how many people do we have? We have N1 plus N2 people. So we had 2,720 that were wearing seatbelts, or excuse me, that were not wearing seatbelts. And then we had 7,783 that were wearing seatbelts. And then we're going to talk about that fatality rate for all of those people. While we had 33 fatalities among those without seatbelts, and we had 17 fatalities among those who were wearing seatbelts. So if we add these guys together, this is going to be 50 in the numerator. And then in the denominator, we have 10,503. And then I want a decimal approximation of that. So I will type that into my calculator, 50 divided by 10,503. And I get approximately 4.7605 times 10 to the negative third. So that's my P bar. And Q bar is just like that, except instead of being the fatality rate, it's the survival rate. It's everyone who survived. So we're just going to take the complement of this. It's 1 minus this answer. Which is approximately 0.995239, and so on. So that's what's going to go over here. We'll have P bar Q bar over N1 here, and P bar Q bar over N2 here, because P bar is our best estimate of that common value of P. And then if those are the same, well then the complement of that Q bar is also going to be the same. So what we want here is P1 hat minus P2 hat, which is this quantity. Minus this difference between P1 and P2, provided that the null hypothesis is true. So this is the value of the mean of the distribution of P1 hat minus P2 hat. If the null hypothesis is true, we're assuming that that's 0. So we're taking this quantity from right here, and then we're subtracting 0, which doesn't do much. Doesn't really do anything, does it? And then we're dividing by the square root of these two fractions. And the sample size for the first sample was 2,720. The sample size for the second sample was 7,783. And then I want P1 hat here, or not P1 hat, P bar here. So that's 50 out of 10,503. And then we want to say, let's multiply that by Q bar. So it's going to be 10,503 minus 50. So that's 10,453. out of 10,503. And we're going to see the same numbers over here. So I'm just going to add little dots. Now, I could try to type all of that in my calculator, and I have done that many times, but I don't think it's necessary when you have technology at home that will allow you to do this. So I'm going to show you how to do this in Excel now. Okay, so I'm just going to enter my data. For my first sample, I had 2,720. Those were the people without seatbelts. 33 died. For the second sample, I had 7,783 people that wore seatbelts. Only 17 of those died. And so P1 hat is X1 over N1. So I'm typing equals X1 over N1. I'm selecting those cells. And then P2 hat is X2 over, X2 divided by N2. And then Q1 hat is the complement of this. So it's 1 minus that quantity. And Q2 hat is 1 minus that quantity. Okay. Now, in order to compute this test statistic Z, what we need is P1 hat minus P2 hat. So I'll enter that here. P1 hat minus P2 hat. So that is our difference. It's what I got on my paper too. That's good. And then the test statistic, that is coming from that formula, but in order to compute that test statistic, we need that pooled sample proportion. So we need P bar. That's our pooled sample proportion. In order to compute P bar, we need our new sample size. So I'm going to have N1 plus N2 in this cell. So that's our new sample size. And then we want the new number of successes. And I almost hate to call it success. I do really hate to call it success when we're talking about fatalities. The successes here. We're adding those together. So we get that. So P bar is X1 plus X2 divided by N1 plus N2. And then Q bar looks just like that, except it's the complement. If this is a fatality rate, Q bar is the survival rate. So we have that. Okay. Now the estimated standard deviation that we're using, assuming that the null hypothesis is true, is this. It's the square root of, and you use SQRT for square root in Excel for that function. And then we're going to have one fraction plus another fraction. The first fraction is P bar times Q bar over N1. So I've got P bar times Q bar divided by N1. Okay, and then the second fraction is P bar times Q bar, close parentheses, divided by N2, close parentheses, and we want the square root of that. That's our standard deviation. So our test statistic Z is equal to P1 hat minus P2 hat minus 0. That's the value of P1 minus P2 assumed in our null hypothesis, divided by the estimate for the standard deviation. So we get a test statistic of about 6.49 if I round to 2 decimal places, and we usually do when it comes to test statistics. That means our P1 minus P2 hat is actually 6.49 standard deviations above the mean, which is pretty surprising, especially given that the difference between P1 hat and P2 hat is 0.0099. That must be because that standard deviation is so small. Okay, so we've got our test statistic Z. Let's enter that in MyLab Statistics. Excuse me, 6.49. Okay, great. And then we want the associated p-value. Now, since we have a z-score that is higher than 3.5, if we use table A2 to find the corresponding p-value, we're going to get 0.001. 0, 0, 0, 1. Actually, let me share my paper with you just so that we can talk through this again. So this picture that I drew is grossly not to scale. P1 hat minus P2 hat is actually 60 standard or 6.49 standard deviations above the mean. So I'm just going to draw it over here. See, that one's wrong. Maybe it's closer to that. And the p-value is related to this area in the tail. Now, in order to decide if that's the p-value, we have to look at the alternative hypothesis. Since the alternative hypothesis involves a greater than sign, which kind of looks like an arrow pointing to the right. We know this is a right-tailed test. So that means the p-value actually is this area in the right tail. If that was a not equal to sign, we'd have to find the area in the right tail and then double it. So we've got P1 hat minus P2 hat here, and we're wondering what is the probability of getting a P1 hat minus P2 hat equal to ours, or a P1 minus P2 hat that's greater than ours? Well, that is the same as the probability of getting a test statistic Z equal to ours, which was about 6.49, or a value that's greater than that. So this p-value, that probability, that area under the curve is the p-value there. Well, that's the same as this area over here. So when we compute this, what we're actually computing is this. Now, if I use table A2, they're going to tell me that this area is 0.0001. And if you're saying to yourself, how do you know that? Let's talk it through. So using table A2, we have the p-value is the probability that Z is greater than or equal to 6.49 approximately. Well, using table A2, we don't have areas to the right, we only have areas to the left. So if I want an area to the right, I have to actually take 1 minus the area to the left in order to find that. And then I look this z-score up in my table, and then I look for the entry in the table that tells me the area to the left of that particular z-score. So here are my positive z-scores. Notice that they only go up to this 3.5. So when I'm using table A2, I go to z equals 3.5 and up, and they're telling me that the area to the left can be approximated by 0.9999. So they're saying this is equal to 0.9999, and we're subtracting that from 1. So that's going to give us 0.0001 as our p-value. Now, if we want to be more accurate, we can use Excel. And we're going to have to do the same thing in Excel because Excel only gives us area to the left as well. So we'll find the area to the left of our z-score, and then we'll subtract that from 1, and then we'll see what we get. Okay, so using Excel, if I want the area to the left of this z-score, actually I want the area to the right, but we can only compute the area to the left, at least initially. I'm going to use the norm.dist function. So we type equals norm.dist, open parentheses, and then choose your test statistic. And then you want the mean of that distribution. Well, it was a standard normal distribution, so the mean is 0, the standard deviation is 1. And we want to say, yes, true, I want the cumulative area to the left. And they say the area to the left is 1. So the p-value, which is the area to the right, is going to be 1 minus this answer. I'm wondering if it's just a decimal approximation, so I'll just actually do the computation, and there we get our p-value. So the actual p-value is tiny. Using Excel, we've got a p-value of 1 minus norm.dist of that approximation 6.49 for a standard, or for a normal distribution with a mean of 0 and a standard deviation of 1. And that is approximately 4.33 times 10 to the negative 11. So I want to share this with you on my paper. I just want you to be aware of what that is. That's 0.0000. It's 4 zeros, 5, 6, 7, 8, 9, 10. And then in the 11th place, we're going to write that 433. That is the probability of getting a P1 hat minus P2 hat, provided that P1 and P2 are equal to each other. That is clearly ridiculously small. And if I'm rounding to 3 decimal places, as they want me to in MyLab statistics, we're going to enter that. So whether you use table A2 or you use Excel to get a more accurate answer all the way out to the 11th decimal place there, we see that P is very small. So for rounding to 3 decimal places, we type 0.000, which means we have a tiny, tiny probability of getting a P1 hat minus P2 hat like ours. And then we make a conclusion for the hypothesis test. So we compare this p-value, which is basically 0, to the alpha value, which is 0.05. Clearly the p is less than alpha. And since p is less than alpha, we're saying that it's highly improbable to get a P1 hat minus a P2 hat that we got, provided that the null hypothesis is true. So the null hypothesis is probably not true. Let's reject the null hypothesis. Now, in order to make a final statement about the original claim, we need to think about these null and alternative hypotheses that we talked about at the beginning here. So we need to focus on this and then how that relates to the original claim. Now, the claim is the second one. The claim happened to be the alternative hypothesis. So when we reject the null hypothesis, in this case, we're actually supporting the claim. So I'll clear that out. That means there is sufficient evidence to support the claim that the fatality rate is higher for those not wearing seatbelts than the fatality rate for those wearing seatbelts. Okay, and now we want to test the claim by constructing an appropriate confidence interval. I will share my paper with you again, and this time we want to round to 3 decimal places as needed. Okay, so we want a confidence interval, and that's an interval that's going to have this form. Now the center of the confidence interval is our best point estimate of P1 minus P2, which is P1 hat minus P2 hat. We've already computed that. P1 hat minus P2 hat is this value minus this value, which is equal to this. It's approximately equal to this. That's in the middle. And then we want to add and subtract that margin of error. And the margin of error has to do with the significance level of our hypothesis test, whether the hypothesis test is left-tailed or right-tailed or two-tailed. And it also has to do with the estimated standard deviation for our distribution. So the error, or the margin of error, turns out to be equal to this. It's typically notated by z sub alpha over 2 times the square root of this expression here. Now, this came from the same place that this formula came from, but this formula for the standard deviation is a little bit different, because instead of having a P1 and a Q1 and a P2 and a Q2 here, we replaced P1 and P2 with P bar, and we replaced Q1 and Q2 with Q bar because we were assuming that P1 and P2 were equal to each other. And we said that our best estimate for P1 and P2, which are equal to each other, is this pooled sample proportion, which is just making a big proportion out of those two proportions and then finding out what that is. Now, when we construct a confidence interval, we're not making an assumption like that at all. So rather than using P bar and Q bar here, we're going to use P1 and Q1, but we actually don't know those either. We're trying to estimate P1 minus P2. Since we don't know these, we're going to use our best estimate for what those are. So we'll use P1 hat and Q1 hat. And then this is going to look very similar, but you're going to have subscripts of 2. So you'll have P2 hat and Q2 hat over N2. So the standard deviation has almost the same form, but because we are not making any assumptions about P1 and P2, we're not saying that they're equal to each other. We use P1 hat and Q1 hat and P2 hat and Q2 hat as estimates for P1, Q1, and P2 and Q2. Okay, so I will use Excel to compute this for us, and then I will talk through how we find the appropriate Z sub alpha over 2. Let's use Excel to compute this piece first. Okay, so I'm going to use a lot of the same statistics that I had from earlier, but this time I'm not going to use P bar or Q bar or this N1 plus N2 or X1 plus X2. None of this is needed whenever we're computing a confidence interval. So I'm just going to clear the contents there. But I will need P1 hat and Q1 hat, P2 hat and Q2 hat, and N1 and N2. So our estimated standard deviation this time is the square root of, open parentheses, P1 hat times Q1 hat divided by the sample size there, plus, open parentheses for that numerator of the next fraction, P2 hat times Q2 hat divided by the sample size over there. So that's that. Now, when I want the margin of error, I need to take this estimated standard deviation and multiply it by Z sub alpha over 2. Well, what that Z sub alpha over 2, I should say Z sub alpha over 2, will be does not depend on alpha anymore. We have to be really careful because the alpha used for our significance level in our problem statement is not necessarily the alpha that you're going to use over here. You have to think very, you have to be very careful and make sure that you think about whether this is a two-tailed test or a one-tailed test before you compute the appropriate Z value. So I'll share my paper with you so that we can do that together. Okay, so we go over here to our null and alternative hypotheses, and we see the alternative hypothesis has a greater than sign. So it's like an arrow pointing to the right. So that means this is a right-tailed test. So we've got a right-tailed test, and it was associated with a certain significance level. Oops. Since it's a right-tailed test associated with a certain significance level, the area in that top right tail is going to be the alpha that was given in our problem statement. Now, the alpha given in our problem statement was over here. Let's see. It says use a 0.05 significance level. So alpha is 0.05. But remember, whenever you compute a confidence interval, it's always two-tailed for a confidence interval. You're always looking at some area in the middle. So if the area in the right tail is 0.05, we want the area in the left tail to be 0.05 as well, which means you've got 5% of area in the top tail, 5% of the area in the bottom tail. That means you're going to have the 90% of the area in the middle. So this is going to be a 90% confidence interval. Or we're computing confidence interval at the 90% confidence level. And Z sub alpha over 2 is this Z score. So it's actually not Z sub 0.05 divided by 2. It's actually Z sub 0.05 because it was a right-tailed test. The area to the right is 0.05. Okay, so in order to find that Z score, what I need is the Z score that gives me an area to the left, or excuse me, an area to the right of 0.05. That means the area to the left is, of course, the complement of that, or 0.95. And we could use table A2. That's one way of finding that Z score. Or we could use Excel. So if I'm using table A2, I'm going to go to my table and I'm going to look for 0.95 in the body of the table. Okay, so I'm looking for 0.95 in the body of the table, and I think we can see that the closest that we're going to get are these two values right here. So I've got 0.95 or 9495, and this one was 0.9505. So it's right in between. And if we follow this, we see an asterisk there. if we follow that to the footnote in this table, oops, sorry about that. We see that if we want an area to the left of 0.95, the corresponding z-score is z equals 1.645. Now we could get the same value using Excel. Let me show you how to do that. Okay, so the function that we need in Excel is an inverse function because we're giving them an area to the left and we're wanting a z-score. So we'll type equals norm dot s for standard normal distribution. And we don't want that first one, we want the inverse function. So we want norm.s.inv. And then if you open the parentheses, Excel will give you the command that it's expecting a probability. Again, that probability is an area. Probabilities and areas are interchangeable in this class. And we want the area to the right, or excuse me, the area to the right to be 0.05, which means the area to the left is 0.95. And we get 1.64. But if we go out to 3 decimal places, we get 1.645, which is the same value that we got when we used table A2. So we have got the same value using Excel that we got using table A2, just the value in Excel is a little bit more accurate. So we can round out to multiple or to many decimal places. I'm actually not sure where the accuracy ends, but it's going to be more accurate than what we can get using table A2. Okay, so our margin of error is this z-score times that estimated standard deviation. So I will type z sub alpha over 2 times this estimated standard deviation, and we get that for our margin of error. So the upper limit for a confidence interval is p1 hat minus p2 hat plus the margin of error. And the lower limit is p1 hat minus p2 hat minus the margin of error. And if we're rounding to 3 decimal places, we get those two values right there. Okay, so I've just written down everything that I had in Excel over here. Okay, so that's my upper limit and my lower limit. Let's go type this into my lab statistic. So the lower limit is 0.006 and the upper limit is 0.014. Okay, great. And then it asks us, what is the conclusion based on the confidence interval? And basically, we're going to see whether or not that confidence interval includes the value of 0. Since P1 minus P2 is likely to be between 0.006 and 0.014, that confidence interval does not include 0. Since it doesn't include 0, it's not including that value P1 minus P2 equals 0 from the null hypothesis. So that is telling us that we have evidence that suggests that P1 and P2 are not equal to each other. So that appears that the two fatality rates are not equal. Then it says, because the confidence interval limits include only positive values, it appears that the fatality rate is higher for those not wearing seatbelts. Because remember, P sub 1 is the proportion of people who died, or the fatality rate for those not wearing seatbelts. So if P1 minus P2 is always positive, that's saying that P1 is greater than P2. So P1 would have to be higher in that case. Okay, it looks like we've got one more question. And then it says, what do the results suggest about the effectiveness of seatbelts? Then it says, the results suggest that the use of seatbelts is associated with higher fatality rates. No, that's not true. The results suggest that the use of seatbelts is associated with lower fatality rates than not using seatbelts. Yes, that's true. The results suggest that the use of seatbelts is associated with the same fatality rates. No, that's not true, or the results are inconclusive. So B is our answer.